Okay, in the last lesson, we started talking about areas under curves and wondering what the significance of the area under a curve might be. So let's start exploring it a little bit. Let's say we've got ourselves a function, say something like this, call it f of x. And suppose we're interested in the area under the curve of the graph of f of x and above the x-axis. So basically between the curve and the x-axis on the interval from a to b. Now if we had something simple like this, we'd be able to do it easily, right? We'd take the height, multiply the height by the width here, and multiply this height by the width, and we get the area underneath the curve. Even if we had a triangle or something like that, we'd be able to use some geometric properties of trapezoids and triangles and so on to figure that out. But if you have some curvy curve like this, then how do we go about finding the area, or at least finding an approximation for the area? And so what I suggested last time when we were talking about that velocity problem was doing something like this. Let's take this interval and let's break it up into a whole bunch of little subintervals. They don't have to be the same size. No reason why they shouldn't be, but they don't have to be. Something like that. And we'll call each one of these little subintervals. This one here will be let's see, this will be x sub 1. This could be x sub naught if we want to get some nice notation. X sub 2, x sub 3, all the way up to this one here would be x sub n. And if we wanted to, we could talk about the little distance from one of these to another. So this little distance right here, from here to here, would be delta x sub 1. That's the distance from x1 to x naught. And this right here would be delta x sub 3. And this one right here might be a generic delta x sub k, and so on. This one right here would be delta x sub n. So those are the widths of the base of these different little intervals. So here's my plan, is that for each one of these little intervals we choose a point inside. And again, we've got a lot of liberty. If we want to, we can always choose the left end point, we could choose the right end point, we could choose the midpoint, we could choose just basically any point we want. Just for sake of uniformity, I'm going to choose the left endpoint this time, just so you can kind of see easily what's going to happen. And for each one of these intervals, I'm going to then, since I'm choosing the left endpoint, I'm going to find the value of the function at that point, and then make a rectangle which has that as the height. And then, of course, the base is going to be the base that we've already determined of this little interval delta x1. So right there is the area underneath this first little rectangle. Do the same thing here and fill that in. And the same thing here. Fill that in. Do the same thing here. Make them different so you can see them. Here, notice it's going to come out like this. And so on. And you get the idea. Go all the way across. So notice that some of these rectangles are going to be a little bit underneath. They're going to be a little less than the area underneath the function on that little subinterval. Some of them are going to give us a little area of a region larger than the area of the region under the rectangle. But the key is, here's the key, that if we let A stand for the area, let's just make a big A here that stands for this whole area here. A is going to be approximately what you get by, here's summation notation, adding up all these rectangles. Each one of these rectangles, the height of it is going to be f of x sub k. Let's see. I guess it's going to be k minus 1 because I'm choosing the left-hand endpoint. And then I multiply that by the width of the interval, which is a little delta x sub k. And we're going to add all these things up as k goes from 1 to n being the largest, the greatest one, and x naught being the least one. So basically, this is summation notation. I can't remember whether we've used this in class before. Let's just, I'll give you a quick lesson here. If I wanted to add up, for example, 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed, the notation for that is just to use any little symbol I want at all. Let's just say k cubed, k going from 1 to 5. And so this is just saying whatever this little symbol is, I'm going to do that. I'm going to do this to each of the numbers from 1 to 5. If I changed it to a n instead, it would be exactly the same thing because it's called a dummy variable. Doesn't matter what that is. It's just telling you what to do. Okay, so that's summation notation. So this is summation notation, right? Because we're just adding up all of these intervals. I mean, all of these rectangles, the areas of all these rectangles. So the first thing I want you to note is that what we have here is going to be an approximation. Do you agree? An approximation for the area underneath the curve. The second thing I want you to note is that approximation is going to get better as the size of these rectangles get smaller. Do you agree? It's kind of hard to do it. I do have a green here. If I took all these and broke them in half, so that now you break that one in half, and now this one is going to go from here to here, and then from there to there. So we're leaving out that much. So if you do that all the way through, the more you do it, the more you're going to be leaving out the extra stuff, or you're going to be gaining extra stuff as you need it in here. The point is you're going to be getting closer and closer. So that's key. And then because of that, here's what we can finally say then. We can finally define that the area underneath the graph of this function from a to b, we'll define that to be the limit. Here's this important word, the limit of these things. Now, how should we say it? Is it the limit as n goes to infinity? That would work if they were all the same size. If they were all uniform, then as n went to infinity, they would all have to keep getting smaller and smaller and smaller. Recall, though, I said they didn't have to be the same size. So in order to force all these things to get to, which is what we want all of them. We don't want a whole bunch of them to be real small in here and then have one great big one out here which still has a lot of error. We want all of them, all of these widths here to keep getting smaller. So the notation we use is like this. Put a double, that one didn't show up very well. Okay, I'm just going to get rid of that right there. It goes to 0. This stands for the greatest length. The greatest length, the length of the largest one goes to 0, which means they all have to be going to 0. So it's basically just saying they're all going to 0. As they get smaller and smaller and smaller, you're going to be getting closer and closer and closer to the true value of the area underneath that function. Okay? So, recall what we did with derivatives. We started off by saying here we've got this sort of thing, and we want the slope right there. So what did we do? We took delta y over delta x. That was the slope of the secant line. And then we basically took the limit of delta y over delta x as that delta x went to 0. And we said as this limit goes to 0, basically you're finding no longer the slope of the secant line, but you're finding the slope of that tangent line. And we call the slope of that tangent line dy dx. So we basically, as we went from a finite distance to an infinitesimally small distance, we switched the notation from delta to d. And so we're going to do something similar here. We want to capture the idea that these things are getting infinitely small. So here's the notation we use. We first of all still want to indicate, we still want to indicate our function. So here's our function. That's the thing that we're working on. Now we want this thing to be infinitely small. So just like this thing became a dx, we're going to let those things become little dx's. And now instead of summing up just a finite number of things, we're going to think of summing up an infinite number of all these little things. That's really what we're doing here. We're taking the limit as this thing goes to 0. So it's essentially like taking the limit of an infinite number of tiny, tiny, tiny small rectangles. And so we need something other than a summation sign, but we still want it to capture the idea of sum. So what we do is, the word sum starts with s, and so we take the s from sum and we elongate it and make it into a big, long s like that, and it's called the integral sign. And we basically say we want to add up, we want to sum up all of those rectangles as x goes, in this case, from A to B. From A to B. So this thing right here, a lot of notation. This is called an integral sign. Integral, let's see, why do we use the word integral? To integrate things often means to kind of add a bunch of ideas together. If you're integrating ideas, you're adding them together, and I guess that's maybe the idea. Integral sign. This whole thing is the integral. These are the limits of integration. Tell you where to start. Limits of integration. This is the integrand. That's the function that you're integrating. That's the function for which you're finding the area underneath. And then just like this thing here was a dummy variable, this x is also a dummy variable. Okay, that's still a dummy variable. It could be anything. The value doesn't change. The value doesn't change whether we have an x in there or a t or a z or anything else. It's a dummy variable. It's just telling you what to do. It's just telling you what to do. Okay? So this is what this means. This stands for the area underneath this curve from A to B. As yet, we don't know how to find it, but that's what it stands for. Okay? That's what it represents. So let's get that down solid, and then we will discover how to find it. That's ultimately what we're after, is trying to find the area underneath curves. So suppose you have a situation like this. Say you have a function from here to here, and let's say the function goes down and up and way up like this, whatever, just crazy like this. Let's say that this is -7, this is -3, here's 0 obviously, here's 2, here's 8, here's 10, and here's 14. Okay, and so this is the function f of x. Okay, and let's say that the area of each of these little globs, let's say that the area underneath this one is, say, 6. And let's say that the area of that little glob is 4. This one looks pretty big. Maybe this is, let's say it's 13. This one looks a little smaller than that. Let's say it's 3. And this one looks like maybe it's 8. Oh, let's make it 9. Just to make sure I've got an 8 right there. Okay? So, let's just make sure you're solid with me on this. If we were to write what's the integral of f of x dx from -7 to -3, the value of that would be, what's the area? The value of that would be 6. If we were to find the value of the integral from -3 to 2 of f of x dx, what would that be? Well, notice that the area is 4, and I've been using the word area so far. But let's think about again what this thing actually stands for again. Let me do it over here. The integral is the limit of all of these little rectangles. Agreed? The limit of all those rectangles. And all those rectangles, let's think about them. What's going on here? Each one of those rectangles, the value of f for each one of these things is going to be negative. Agreed? From here to here, the value of f is going to be negative throughout. So you multiply all those negative values times these little dx's there, and you're going to be getting a negative number. So the value of this integral from here to here is not 4, but it's -4. Okay? How about from 2 to 8? Dx, that's going to be 13. Okay. What about from 8 to 10? That's going to be what? -3? What about from 2 to 10? From 2 to 10, well, from here to here, you're getting all these positive contributions adding up to 13. From here to here, you're getting a bunch of negative contributions adding up to -3. So by the time you go from here to here, it's going to be 13 minus 3 is going to be 10. Agreed? See that? So that's the way it works. Let's do something else, which is kind of strange. Let's go from 8 to 2. From 8 to 2. Well, f of x is certainly a positive number all the way through here from 8 to 2. However, again, if you kind of think of this, what are you doing? You're taking the value of the function and you're multiplying it by the width of this little interval, where the width was this endpoint minus this endpoint. It was the right endpoint minus the left one, right? It was this value minus that value that gave us the width. Now we're going in the opposite direction. So you can almost think of these little delta x's as being negatives because you're going from right to left rather than from left to right. So anyway, the bottom line is, if you go in the opposite direction, then it's the negative of this answer. So since from here to here was 13, from here to here is going to be -13. Okay, see that? So let me throw another one at you. How about from, running out of space here, how about from 14 to 10? From 14 to 10 is going to be what? -9? Because you're going from left to right. Okay. How about from 10 to 8? From 10 to 8, well, let's see. It's negative, but you're also going backwards. So it's going to be negative of a negative, so it's going to be back to, let's see. From here to here would be -3, so from here to here would be +3. So it's going to be +3. Okay, one more. Here's say 6 right there. What would be the integral of f of x dx from 6 to 6? From 6 to 6. Well, if we're thinking at all of being the area underneath this curve just over this point, there's only one number you can give to it. and that number is 0. To give it any number other than 0 would be to indicate that you've got some area there, and you don't. Okay, it's just a straight line. So that's from 6 to 6. Okay? So, with that, let me show you a couple final things here. And that is, because of the way this all works out, here's what's true. What's true is that the integral of f of x from a to c, or let's say from a to c, is going to be equal to the value of the integral from a to b plus the value from b to c. And that doesn't depend at all on the order of a, b, and c. Let's look at some examples. Let's get rid of this one for the moment. If this is a, this is b, and this is c, we're saying that the integral from here to here is the value of this one, and then plus the value of that one is going to be 10. We already did that one. What if we took the value from 2 to 8? I'm just going to leave it without putting all the stuff here, just for simplicity. And we said, oh, using this formula, that's going to be the integral from 2 to 10 plus the integral from 10 to 8. Notice they're not in linear order here. Is that still right? The integral from 2 to 8, that's that stuff here. That's 13, agreed? Is that equal to the integral from 2 to 10? First of all, what is the integral from 2 to 10? From 2 to 10 is going to be 13 minus 3 is going to be 10, plus, what's the integral from 10 to 8? Well, from here to here is going to be a negative of a negative 3, so it's going to be plus 3. So sure enough, you get 13 on both sides. See that? So no matter what order you do it in, it's always going to work. Okay, let's just do one more just to show you. Again, if you take the integral from 8 to negative, well, let's say from 8 to 2, that's equal to the integral from 8 to negative 3 plus the integral from negative 3 to 2. As long as those two match, let's see if it's right. From 8 to 2, that's going to be what? That's going to be a negative 13 on this side. On this side, we're going to go 8 to negative 3. Let's see, what's that going to be? 8 to negative 3. This is going to be a negative 13. And then this is going to be a positive 4. Negative 13 plus 4 is a negative 9. And then how about from negative 3 to 2? From negative 3 to 2 is a negative 4. From negative 3 to 2 is a negative 4. So sure enough, negative 13, negative 13. So that's important. The other thing I'll just mention to you is that if you have two functions, so say this is f, and here's the function g right here, then the area from a to b, let me change the picture now. Here's f. Say there's g. The integral from a to b of f of x plus g of x, that's going to be equal to the value of the integral of f of x plus the value of the integral of g of x. Do you see why? Because if this is the function f and this is the function g, then what's f plus g going to look like? I didn't leave enough space for it up here, but f plus g is going to be up here someplace, right? It's the sum of these two. Let me do that just a little bit better. Let's say that f looks like this, and let's say that g looks like this. So f plus g is going to look kind of roughly like that. Okay? So the point is, if you find the area or the value of the integral underneath f plus g, it's just what are you doing? You're adding up all those little rectangles, and all those rectangles, each one is the length, this rectangle right here, the area of that is going to be basically the sum of this rectangle plus the big one, right? You take the smaller one plus the big one, you're going to be right there. So you have that. And similarly, if you have a function f, and so 3f would be like this, then the integral of 3 times f of x from a to b, can you see it? How does the area underneath this thing compare with the area underneath this? Well, all these heights are exactly 3 times as big as that, so that's going to be just exactly 3 times the integral of small f from a to b. Okay? So, there's kind of everything there is to know about integrals, and I've shown you everything about them except how to calculate them, and that's ultimately the thing we want to do. We want to be able to, given a function, find out what is the value of that area. Find the value of the area. That's what's coming up next time.